All right. Oh, yeah, I'm recording now. Okay, so we're going to talk about section 6.4, arc length. Let me give you a moment to copy the example down. Okay, so let's take a look at what we have here. Now, is there any kind of arc that you have learned about that you can find the length of? Is there any kind of arc that you know how to find the length of? Let's say, well, a circle. That's right, Victoria. The circumference of a circle. That's right, Opiendi. So the circumference of a circle is 2 times pi times the radius. Okay, so and also, what about like if you had a what if you had an arc? I usually like to draw my arcs in red. Traditionally, I like to draw the arc in red. Whoops. What about that arc there?
But that's just a straight line. I mean, we
That's
know how to
right.
find it, but we cannot call it an arc, right?
Well, it's an arc. It's just a line segment, but there are all kinds of arcs. There are all kinds of
Okay.
arcs, and the arcs can be generated using parametric equations like this to draw the arc. How many recall parametric equations from their pre-calculus days?
Yeah.
Yeah, and I will review that real quick. So what we're going to do is we have a curve described by these parametric equations. So what happens is, you see, a curve, right, has coordinates, has these coordinates. And, you have an x coordinate and a y coordinate. But what we're thinking about now is, okay, we have an x and y coordinate. Let me start fresh here on this. So here's some arc, okay, and maybe it's like a fixed length. I mean, it wouldn't make sense to find the length of an arc if it weren't a fixed length, right? So you have a coordinate on the arc. And of course, coordinates are xy coordinates. But now we're saying let x be a function of t and let y be a function of t. And as t varies, you trace out an arc. And the arrow on the arc, that red arrow on the arc right here, or this arc C, that red arrow means as t increases, the arc goes in that direction. So for this problem here, they're saying that the arc that we want has parametric equations given by x equals t squared and y equals t cubed. And they're saying that the point 1, 1 is on the arc. That's your starting point. Why is 1, 1 on the arc? What value of t would have to go for what t is the parameter? What's the value of my parameter when the arc is at point 1, begins at point 1, 1?
1.
That's right. What, Clea?
I just said it's 1.
That's right. So Clea and Yonatan and Mohammed agree. T equals 1. That's right. Because you know, 1 squared is 1. That's the x coordinate here, right? 1 squared is 1. And y is t cubed, so 1 cubed is also 1. So clearly, t equals 1 helps you begin. Now, let's talk about the endpoint here, 4, 8. What would t be there for the coordinate 4, 8? Good, Yonatan. T would have to be 2. T would have to be 2. All right. Are there any questions on that? Any questions on the, you know, because you see, we're going to have a formula for the arc length. We're going to have a formula, but we need to know the t limits, the beginning t limit and the ending t limit.
Professor, so
yes, go ahead.
Yeah, so like here the t is, when we find the t, we're finding the x, or like, or it doesn't have anything to do.
You're finding the beginning, so the parameter t takes on different values, and as t takes on different values, based on these parametric equations, these parametric equations here, you generate different points on the curve. You generate all, you know, different points.
Oh, okay, I see.
And now the t equals 2, so, you know, what value of t would give us 4, 8? Well, x is, we're required to have 2 squared, right? That's the formula. X equals t squared. And y is t cubed. So let's see, would 2 cubed be 8? Yeah, it would. So it's like you have to sort of guess a little bit to figure the beginning and ending time values, but it'll work out. And let's see what this curve looks like. Okay, so what I'd like you to do, let's go to Desmos, and we're gonna find out what this particular arc looks like that can be described by those two parametric equations. So I'm going to Desmos here. Okay, I'm going to Desmos. Let me see here, one moment. Okay, can everybody see Desmos okay? Is it showing up okay?
Yes, Professor.
Good, good. Okay, so here's what you do. So parametric equations, we're going to graph that curve. So we use a left parenthesis and we type t squared. and then a comma, and then the y coordinate is described by t cubed. Okay? And you see already it's drawing a little picture, and well, we want t to go from 1 to 2. Okay, and it looks like the picture, we've cut off a part of our arc. So we can move down a little bit here and center things, and you can make things bigger, you can make things smaller. You have a wrench there that allows you to really control your axis. But I think this is fine. Are there any questions on this? Any questions? You can see that the arc starts at the coordinate 1, xy coordinate 1, 1, and ends up at the coordinate xy coordinate 4, 8. And if we had to guess the length of that arc, with the grids there in decimals, which is kind of nice, if we had to sort of make a guess, a good guess at what the length of that arc is, how long? What do you think the length would be if you had to take a guess? Would it equal 10? Okay, so definitely not that much. Jasmine, Shalom, and Yonatan are giving, and OPME are giving estimates between like 7 and 7.5 and 8.5. So that's probably a good ballpark number. OPME says 8.9, and we'll see. So on like when you do these kind of problems from section 6.4, it's always helpful to I want to say it the right way, it can be helpful to use decimals to give you an idea of what a reasonable length is. But given that, now what we're going to do is we're going to find the exact arc length. Are there any questions before I move on here? Okay. Well, let me go to the whiteboard, and I'm going to write down the formula for arc length. Okay. So this here, what we're doing here, this is again, we're in section 6.4. The length of the arc is the integral from A to B, where the integrand is the square root of dx dt quantity squared plus dy dt quantity squared. And then you're integrating with respect to t. So we're assuming here that x is some function of t. Well, the way they write it in the book, I want to make sure. Let me find it here in the textbook. One moment. Hold on. So it's in section 6.4, and it is the first formula. So they say, okay, if f is some function f of t and y is some function g of t, then the arc length, and you have a starting time A and an ending time B. So like in the example we're doing, the starting time is t equals 1, the ending time is t equals 2. The length of the arc is given by the integral of the square root of the sum of the derivatives of x and y with respect to t squared. So we dx dt squared plus dy dt squared. That's the formula. And you should know that formula. That formula is, they prove it in the textbook. They prove it in the textbook on pages 455 to 456. And if we have time in class later today or on Monday, we'll have class on Monday. I can show you the proof. But for now, let's sort of focus on the problem at hand here. Okay, so let's go ahead. Let's go ahead. Yeah, this is dy dt. Let's go ahead and get to the problem and work it out. So okay, so here's our, here the arc is described by these parametric equations. The arc goes from points 1, 1 to 4, 8. So what I've done here in the solution, okay, is on the right, I drew a little picture, but this picture really, I mean, all I did was I mean, we drew this picture in Desmos, and these here, like if you're using a TI-83 or 84 calculator, you have to put your calculator in parametric mode. And then like the T window would go from 1 to 2 with a scale of 0.1, that would work fine. And then the X window could go from 0 to 10 with the next scale of 1. And the Y part could go from 0 to 10 with a Y scale of 1. So, you know, you can graph curves defined by parametric equations in your TI-83, 84 calculator. Certainly, it looks like Desmos is very convenient though as well. All right, and this here, that's just the picture we saw in Desmos, right? Okay, so let us see now. Let's start off. Let's start off with this here. One moment here. So remember that x is equal to t squared. So that means dx dt equals 2t. And so this is how you get that 2t. Okay, and so you're taking dx dt squared. Okay, so we know what dx dt is. Now the y equals t cubed, right? So dy dt would be 3t squared. And there's the 3t squared right there. And then we're squaring both the 2t and the 3t squared. So you end up getting an integral from 1 to 2 of the square root of 4t squared plus 9t to the 4th. Please let me know if you have any questions up to this integral here. All right. Well, yes, Susanna.
The squaring the derivatives and then taking the square root, doesn't that sort of cancel each other out? I don't see why it's a necessary.
It normally, it's a good question. It normally would, except you have a plus here. So you can't in other words, the square root of 4t squared plus 9t to the fourth. You cannot write that as like the square root of 4t to the fourth times the square root of 9, or I'm sorry, 4t squared times the square root of 9t to the fourth. You can't do that. Not allowed because of the plus.
Okay.
Yeah, life would be easier, right? If we could do
Yes,
that.
it would.
But,
Okay, thank you.
so, all right, now, good question. And we want to find the exact value for this integral. So we don't want an approximation. WebAssign will count approximation as likely as wrong. And you don't want that to happen to you on the exam, right? Either. So we need to do something with this integral. One thing you might notice right off the bat is that 4t squared plus 9t to the fourth, there's a common factor of t squared. We can factor t squared out. So that would give us t squared times 4 plus 9t squared. And so that's what we have here. Now the thing is, you see, the square root of t squared times 4 plus 9t squared. Okay, hold on here. That will equal the square root of t squared times the square root of 4 plus 9t squared. That's that rule, you know, that says if you have the square root of a times b, that equals the square root of a times the square root of b. And so there we go. And that's what I use. Now the thing is, the square root of t squared becomes t. And so this now gets us to here. See, we have to do something to remove that square root, or, well, not remove the square root, but we got to do something to get this so we can do an integral. So we can get our, integrate. Yes, question.
So, Professor, I get what we're doing until now, but like one thing I don't get is like, why are we still keeping the 4 into the square root? Because like, isn't the square root of 4 2?
It is, but we can't. If you have, I'll show you here. So if you have the square root of 4 plus 9t squared, is that equal? Well, hold on. Let me get. I like to have space when I do things. Is this equal to the square root of 4 plus the square root of 9t squared?
Oh yeah, because we have the plus. Oh yeah, okay.
That's right. That's right. So we're going to have to do this integral, and luckily we've learned some integration techniques. So when we see this integral, well, you've learned about integration, you've learned substitution, integration by parts, partial fractions. Substitution will work here very nicely. If you let u equal 4 plus 9t squared, then it turns out that then du will be 18t dt, because du dt would just be 9 times 2t. So du dt is 18t, and therefore du is 18t dt, and so t dt is 1/18 du. And this allows us to rewrite that integral then in terms of an integral with respect to u. So this integral becomes this integral. So remember, you have a t limit of 1 here. Well, becomes a u limit of 13 because u is 4 plus 9t squared. Well, 4 plus 9 times 1 squared equals 13. Similarly, for the u limit of 40 above, how do we get that? We took 4 plus 9 times 2 squared to get 40. Jonathan asked, do we change our bounds if we do the substitution afterwards? Well, the thing is, I mean, I'm going to get the antiderivative for this problem, and then I'm going to substitute in those u limits. Now, I know I have seen sometimes, even in videos, I've seen where they get their antiderivative, and then they go back and substitute in what u it was, and then put in their old x limits. But to me, it just makes sense to work with these new u limits. You know, this is a definite integral. It's not an indefinite integral. Yeah, good question. Good question. All right, are there any other good questions before we move to the next page? Mohammed, okay. Mohammed's wondering, why do we need to change the u limits after the substitution? Here's the reason why. So looking at this, you have an integral with respect to t here, right? And your t limits are 1 and 2. But if you have a new integral with respect to u, you need u limits. You can't use t limits. Well, u was 4 plus 9t squared. So the bottom limit becomes 13, because how are we getting 13? Because 4 plus 9 times 1 squared, the 1, that's, you know, that's, I'm getting the 1 there. That equals 13. And then the other one, the 40, well, that limit, if you have 4 plus 9 times 2 squared, that equals 40. The 2 is right there. You see that, Mohammed? Okay, good. That's why you have to change those limits. I like to keep my limits in the problem. I don't like to, you know, I don't like to do an indefinite integral and then you know, and then put in old x limits. I like to keep my limits there and work through the problem. It's easier for me, and I think it's easier for a lot of students. But all right, well, let's go now. What are we going to do with this 1/18th here? Well, what do we do with this factor here, this 1/18th? Yeah, we're going to bring it out in front of the integral. That's right, Jonathan. Okay, so here we go. So we're continuing here with the length. We bring the 1/18th out. And the antiderivative of u to the half, of course, is 2/3 times u to the 3/2. And we put in 40 and 13. Let me give you a moment to catch up to here. Let me know if you have any questions. Okay, so now the length here, the length, you could write it as 1/27 times 40 to the 3/2 power minus 13 to the 3/2 power. Web of Science should take that answer. It's an exact answer. But what I've done over here is a lot of times we like answers to have roots in them. So like 40 to the 3/2 here can be thought of as 40 to the 1/2 power raised to the 3rd. That's root 40 to the 3rd. Now let me see, maybe I can put in a little extra step here. Root 40 to the 3rd power equals, root 40 times root 40 times root 40. But then that's going to equal 2 root 10 times 2 root 10 times 2 root 10. If I and so that's going to get you then, that's going to get you 2 root 10 to the 3rd power, which is just 2 cubed times root 10 cubed. Root 10 cubed, root 10 cubed is root 10 times root 10 times, hold on, let's make that a little nicer. Root 10 cubed is root 10 times root 10 times root 10. But, man, I got to make that 10 look nicer. That's, hold on. I like things to look good. Okay, so this is root 10 times root 10 times root 10. But root 10 times root 10 is root 100. And that's just 10. So you get, 10 root 10. Okay, and so hence you get 8 times 10 root 10, that's 80 root 10. Okay.
Professor, do we put the answer just like this with the square root?
Well,
Okay.
either answer, this answer here, this answer, or this answer would be acceptable in Web of Science.
Oh, okay.
Should take them both. And why don't we figure out on our calculators or on Desmos what is 1/27 times the difference between 80 root 10 and 13 root 3. I mean, we thought the length of the arc for this problem would be around 7.5 or 8. So it would be, nice to check the answer to see if this is a reasonable answer.
Professor, I did it. I got 7.63371.
Okay, 7.6.
6.
Let me see here. Let me put this in blue. 7.6631.
No, it's 7.63371.
Okay, hang on. 7.63371. All right, thank you, OPME. So are we reasonably comfortable about our answer? Does this answer make sense? I mean, does this, okay, so Susanna, how many think maybe on the test, maybe, for part 2 of the exam, they might use Desmos to, when they get an answer, they might kind of check it in Desmos to see, maybe draw the curve generated by the parametric equations and sort of see if the answer they get is reasonable. Does anybody think? I don't know. Maybe you wouldn't take the. All right. Susanna says she might take the time if time permits, and Clea. Okay. All right. Well, that's right. That's the answer. Now, let me ask you this. Let me ask you this. What if you got this as your length? What if you work this problem out and you got this? 1/27 times the quantity 13 to the 3 halves minus 40 to the 3 halves. Let's say you did it this way. No, let's say you got this answer. How do you know this answer here, how do you know that that can't be right? How do you know that?
Because we're gonna get a negative number, which doesn't make sense.
That's right. You agree with Jonathan Clay. That's right. So, things like that can be very helpful. They can be very helpful when doing these kind of problems. Um, you know, just to check on the reasonableness of your answers. Okay, are there any questions on this example?
Yeah, I had a quick question. Why did you not plug in 40 and 13 after you did the U substitution?
Oh, yeah, well, I did. Here are the, hold on, Mohammed. I do have 40 and 13 here, and they're getting plugged in here and here into the antiderivative.
So you just keep U the whole time you're solving it, like you don't plug
Yeah.
U back in?
Well, you could do this, okay? You could do this. You could say, okay, I have 1/27 times, so I have my antiderivative. It's 1/27 times U to the 3 halves power. And now U is 4 plus 9t squared. So I could have, okay, 4 plus 9t squared raised to the half power, and then have the original limits of 1 and 2. This would work. See, what I'm doing here is the U, I'm putting back in what U was. U was 4 plus 9t squared. Now I got a function of t for my antiderivative. And so then I'm going to use the original t limits. This would work, but it's more work. I mean, let me ask you this: which looks easier? Which looks easier to compute?
The
Choice
second one.
1 or choice 2?
Yeah, the first one.
I think choice 1 is. I agree with Clay. What do you think, Mohammed? Do you think choice 1's easier?
I mean, it's less work, but it just like it confused me from the beginning because you could have just kept it the same way. Like you solve the integral and then just plug
And
in
then
the
do
original
this,
ones.
like what I'm doing here.
Yeah.
You could do it that way. You could. If you like doing it that way, that's fine. That's fine. I've always kind of I know students at times have expressed a little discomfort with using the U limits in a substitution, but to me I'm going from an integral. It's like I'm moving from my old house to a new house. I'm going to use the stuff in my new house. The t limits were in my old house. My new house has the U limits. I don't know if that's a good analogy or not, but certainly. How many kind of like that analogy? Is that am I getting through to anybody with that, or is that
Yeah, I mean, it makes sense now, but I was just confused when you were solving it.
sure? No problem. No problem. Okay. Well, very good. Very good. Excellent. Excellent. And so I want to do some more examples from section 6.4, but I think we should take a little break here. And I want to give you access to the new 6.4 homework that's due on Monday. So And I have to put a setting in so you can access that. So let me, are there any other questions before I stop the recording? Okay, good questions. All right, I'll stop the recording.